They're mesmerizing when you're looking at them. You can sit and watch the lava fountains for hours and you don't even realize that, several hours have passed that you've been sitting there.
The importance of volcanoes, of course, if we wouldn't have volcanoes, we wouldn't have our atmosphere. That's maybe the most important thing.
What is really down there inside volcano?
Our Earth is filled with liquid rock. It's a gigantic furnace, you could call it.
So what's going on the Reykjanes peninsula now, we might be seeing decades of activity. We're just in the early stages of this.
This process is going on for millions of years. On a divergent plate boundary, you are dragging the plates away from each other. Iceland is the only place on Earth where this plate boundary comes out of the sea. To be able to study something like this in great details, Iceland is very, very ideal.
Volcanic activity on Reykjanes happens in pulses. 800 years ago, there was a series of eruptions that took place all along Reykjanes. In 2021, we had the first eruption since medieval times. But in fact, in 2020, there was an intrusion detected underneath Thorbjorn. So potentially that was the start of this new episode.
The rate we were getting were much higher than anything we have measured before here in Iceland. More than 7,000 cubic meters per second.
This is extremely high. These really are ultra-rapid magma flow rates.
We're living in interesting times. To be a volcanologist in Iceland, with Reykjanes having seemingly awoken.
On the afternoon of the 10th of November, a seismic swarm started in this area that seemed to be indicative of a dike propagation. And the first estimate was showing extremely high magma inflow rates to the dike. We had never seen anything like this before. We thought there must be an error in the data. There was no error in the data, there was no error in the models, and we were indeed seeing rapid magma inflow rates to this dike. By that time, it was also evident that the dike had passed beneath Grindavik. Civil protection then made the very rapid decision that evening to evacuate the town of Grindavik.
What is the most important thing when you have to deal with this kind of a challenge coming from the earth and challenging geology is that the country always needs to put safety first, whether it's the people that live in Grindavik or the visitors that are coming.
Það sem skiptir náttúrulega langmestu máli það að það var ekkert líkamlegt tjón eða afleiðingar fyrir fólk, en andlega hliðin náttúrulega röskuð eftir þetta sjálfsögðu og fólk hefur miklar áhyggjur af eignum sínum, aleigunni nánast.
The earthquake swarm has slowed down from what it was on Friday when the evacuation happened. There are fractures that are running through the town. They are quite visible. Some of them are a meter to 3 meters deep, expanding about half a meter to a meter wide. And some of them are running through almost half the town. Today there was a decision made to let the inhabitants of Grindavik to have some time to get back to their homes to get their personal belongings.
I'm a fisherman. I was at sea, Friday and Saturday and Sunday. I just came home Monday night and I didn't know nothing and I haven't been home or nothing after it happened. We need to go back and get, our marriage paper and something, important stuff. And so,
what's the most important for you right now?
Survive, I don't know, what are we gonna do, after 2 weeks? What's gonna happen? I don't know. Not many people want to live there anymore after this. 3,800 people, where are you gonna put them all?
On Friday, when it started, That was just ridiculous. I mean, it was like we were in a basically in a shaker, and the house, it jumped in the biggest one. I was standing in the kitchen. We were going to make a homemade pizza, and we just the whole house jumped up. Now we really don't know what will happen, if it will be an eruption or if it will cool down or move, or we just don't know.
Will you stay in Grindavik?
I'm on the fence right now.
The Icelandic people are quite really resilient regarding nature, but people are still in shock.
Okay. We leave just before. Just a few minutes before. It was our dream house.
Yeah, I didn't know it was gonna be like that. So.
Did you ever think there would be this volcano?
Yeah, but I thought even if the volcano starts, I can see it out my bedroom window. I thought it would be on the other side, and we would have time to come back and get our stuff, and we would just be somewhere else while it was erupted and then come back. But that is not gonna happen.
We had this intrusion going on just north of Thorbjorn in this area here, and we could see this inflation going on in the GPS, and so this is saying that the ground is moving up with time, and then this dramatic shift is the evening of the 10th of November, and what we can see here is that the ground has dropped by around 40 centimeters. But crucially, the signal of inflation has continued without pause. Today we're flying a drone with a LiDAR that's going to scan the ground and produces a point cloud of that surface. The LiDAR measures the position of the ground, and because we've done multiple surveys, we can compare the surface between the different days and see how the ground's moving. 12 minutes left, so it's a super quick.
Okay.
But maybe a field, I guess, side by side. We're in this complicated situation where the ground is moving constantly, so being able to see how the surface has changed over time becomes very difficult if you can't trust the positions to have stayed relatively the same. This rifting is also taking place alongside shearing, because the North American plate and the Eurasian plate are moving alongside each other rather than just spreading apart from each other. If we've got rifting, then you're creating space in the crust which would allow magma to come up. So you could well have a dike that's being formed as a result of the tectonic activity. So these are ground-penetrating radar profiles, and these lines are where we can see fractures actually at the surface. Before people go back, we need to have a good understanding of where these faults are and what's underneath us. So this area of stronger reflections probably indicates that there is some opening there that's not made it to the surface. So we can see some depth into the ground, but this is only 5 meters. And you know, we could push it to maybe 100 meters. We would lose a lot of the resolution, and 100 meters is nowhere near deep enough to actually see the dike if it's there.
So what our team does here at the Icelandic Met Office is essentially we model the ground deformation data, and here we use a combination of essentially the GNSS observations and also interferograms. An interferogram is essentially the difference between the phase component of 2 satellite images taken from approximately the same location overhead but at different times. This measures ground movement during that time period. This interferogram here, you can see the mass of fringes, which is showing a lot of deformation. I mean, this is meter scale deformation that we're seeing here. And this was the deformation associated with this massive dike intrusion that occurred on the 10th of November.
The current unrest on Reykjanes, we can say that there are probably 80% probability that we will have an eruption. So eruption is very likely, but we don't know when it's going to be. And yet we cannot nail down where it's going to be.
Power station is more like there, right? We need to learn about all the processes that control and influence the behavior of a volcanic eruption in order to be able to predict both timing of an event and a behavior of an event.
What we are trying to understand is what lies behind the volcanoes, how the magma comes up to surface and how it spreads on surface.
The main goal of today is to sample the lava flow and also the tephra that was produced by the fountaining activity at the vents. So we want to get the interior of the lava flow, we want to get the outer salvage of the lava flow, the most rapidly cooled part.
It's very important to get the glass, because glass is a rapidly quenched liquid, lava liquid.
It's part of the overall story that we're trying to get and understand better what's happening underground, how the magma is moving, evolving in the subsurface before it comes up. And also in order to help us understand better how the eruption proceeded, the dynamics of the eruption, the degassing, exsolving those gases from the magma and generating those big lava fountains that we observed in the beginning of this eruption.
We are degassing the interior of the Earth, which generates our atmosphere. No volcanoes, no atmosphere. No atmosphere, no humans, no life.
My main interest in volcanology is studying the chemical composition of magmas or lavas and their crystals, because the crystals, they have their own story and give us an intel of what was happening before the eruption and why the magma was behaving the way it behaved. It's like looking into the DNA of an eruption. It has a lot of secrets in a very small world. You could see if it liked the environment it was in. Was it happy? Did it grow just homogeneously, minding its business, or did something in an environment change? So you could sort of, after an eruption, trace back to what really happened and why, and then to learn then in the future what might possibly happen.
Overall, I can say there are these two big questions. How can we better forecast eruptions, and what is really down there inside volcanoes? We still have a long way to go to combine all the different methods we have to come up with a good estimate of the structure of volcanoes that is consistent with all the observations we have. One way to do that would be to drill into magma, to study the transition better from solid rock to molten magma. We have a project here in Iceland we call the Krafla magma testbed.
We have been utilizing geothermal energy in Iceland for decades now. However, going closer to the energy source, which is always a magma, especially in high temperature fields like here in Iceland, we can increase the energy output of a single well by 10 times. We saw this in Krafla in 2009 when we accidentally drilled into magma. The aim at that point was to drill down to 4 kilometers, but the drill bit always got stuck at 2 kilometers depth. Very surprisingly to everyone, they saw that they got chips coming up to the surface which was glass, and then they realized they were fighting magma. That turned out to be the most powerful well ever drilled into in an area like that. 10 times more energy output from that single well than on the average in this same area.
One of the things that really fascinates me about volcanoes is, for most of the time they're dormant. Things are moving very slow. Nothing happens for decades or even centuries. And then they suddenly kick in and everything happens like 1, 2, 3. When it gets to an eruption, the difference between a very explosive eruption and a weakly explosive eruption can be milliseconds.
Very large volcanic eruptions, they can have very drastic effect. And the last eruption to have really had drastic effect was the eruption of Laki in 1783, which is here in Iceland. And that eruption caused basically global cooling on the northern hemisphere.
So yeah, it's overdue for more than 50 years now. The last eruption happened in 1918. It was quite a big eruption because it broke the ice cap. Every time when the subglacial volcano erupts, basically it creates the glacier outbursts. All the water is carrying some icebergs with itself, sediments, gravel, rocks. Basically that's the biggest issue or the biggest problem for people that live nearby. Katla is kind of like a monster volcano, I would say, because it's hiding underneath Mýrdalsjökull ice cap. So there is about 700 meters of ice on top of it, on top of the volcano. You can see many layers of the glacier. They all represent something. So we have shades of blue colors that represents the high density of ice. White colors on the glacier that are filled with some oxygen, so air bubbles, and then we have the black layers which are filled with volcanic ash. Because of the melted water that is running down from the ice cap, allows more space for the higher parts to move, and all the weight that is pushing all the bottom of the glacier down, it's breaking. You can see it in the shape of a crater.
During the last major deglaciation, there was on the order of a 30 to 50-fold increase in eruptive activity in Iceland. So it's highly likely that the present-day deglaciation will also result in an increase in volcanic activity in Iceland. The question is, though, by how much and when?
What's happening right now in Grindavik is that we have a lava eruption. The lava eruption has gone over the defense walls that were built and the lava crack is on each side of that wall, and we have now houses. The lava has caught, set on fire, and now completely vanished. My opinion is that the half of the town is probably going to go under lava midnight tonight. It's flowing really fast at the moment, and of course I hope I'm wrong, but I think that this is not going to end well for Grindavik.
Það liggur fyrir að húsnæðismálin eru brýnasta málið fyrir mörg hér í salnum. Þannig að sem húsið mitt hefur brunnið, þá hef ég fengið fjárhagslegt sjálfstæði, ég hef fengið vissu og ég geta byggt upp nýtt heimili og þessi snara sem utan mig væri farin. Ég vil að þið skilja þetta. Actually, first I told everybody how I'm feeling about this situation and just how hard it is for us to have no certainty what the future is going to look like, both financially and mentally. And then I asked the question, at what point will they consider buying everybody out with the possibility of we will buy the house back when it's safe to go back home, because it's going to be years, not months, until we can go home.
What we are clearly seeing now is continued magma inflow, and while that continues, the diking events and eruptions are very likely to also continue. Future dikes are obviously likely to propagate in the similar areas as to where we've had these most recent propagations since the 10th of November. And since 2 of these dikes have already gone beneath Grindavik, then it is likely that additional dike propagations will occur there. And of course this will cause more damage if this happens.
The pattern of volcanism here seems to be like that. It's confined to volcanic periods where you have frequent eruptions over 300 to 400 years. And then the peninsula goes quiet for 600 to 1,000 years. And then you have another period. And it so happens, and that's actually quite significant, a new volcanic eruption period began in 2021. And what we are seeing today happening near the town of Grindavik is part of that development.